Okay, welcome back. Bear with me while I try and get this organized, straightened up. Okay, that's a bit peculiar. Okay, it's okay. So I'm just having a little bit of discussion with the camera at the moment. All right, welcome back. What I want to look at today is something called solid mechanics dynamics, and this tutorial is on damped vibrations. I repeat, damped vibrations. Okay. Now, this work covers elements of the syllabus for the Engineering Council exam D225, Dynamics of Mechanical Systems, C105, Mechanical and Structural Engineering, and the EDEXCEL HNC/HND module Mechanical Science. Now, I did mechanical science myself in regards to the elasticity of materials, etc. Okay, most materials have a given elasticity. Okay. So my camera just looks a bit peculiar. Okay. Right now, on completion of this tutorial, you should be able to do the following. Define a free damped oscillation, explain the purpose of damping, define damping coefficient, define damping ratio, derive formulae that describe damped vibrations, determine the natural frequency and periodic time for damped systems, define amplitude reduction factor, calculate damping coefficients from observations of amplitude. Okay. Now, this tutorial covers the theory of natural vibrations with damping and continues the studies in the tutorial on free vibrations. To do the tutorial fully, you must be familiar with the following concepts: simple harmonic motion, free vibrations. So it's asking that you've done some units on this before, okay? Or have had some work in regards to this type of work. Right, introduction. In the tutorial on free vibration, it was explained that once set vibrating, the system would carry on oscillating forever because the energy put into the system by the initial disturbance cannot get out of the system. In reality, the oscillation always dies away with time because some form of friction is present. The diagram shows a displacement time graph of a typical damped oscillation, okay? And this is the graph to which we are referring, okay? Now, some of you may not remember, I think it's something called the Catterton Bridge, where it began to sway in high winds, and it began to sway so much that the vibration of this swaying caused the bridge to actually collapse. Now, you would have thought that being engineers and they had built that bridge, that they would have taken into consideration the fact that if the bridge begins to sway, oscillate, that it was going to self-destruct. But even engineers, professional and qualified, highly qualified engineers, can make mistakes or overlook something as simple as vibration. Okay, but it's on. I think it's somewhere on the internet anyway. Okay, where you can see this. The bridge collapsing, of course, not this specifically. Okay, but here you can see that once it started here, the vibration began to pan out, peter out, and fade away completely. But in saying that, the vibration in this case was dissipated through heat or by the material absorbing certain amount of the energy. But in the bridge case, it didn't absorb any energy, it had no place for that energy to go except to within itself causing destruction. Okay. Friction dissipates the energy as heat. Such vibrations are called free and damped. The type of friction that is easiest to deal with mathematically is that created by a dashpot, also called a damper. Let us now examine two kinds of dashpots. Here we will examine dashpots for linear motion. The diagram shows two types of dashpots, air and oil. Air. The piston moves inside the cylinder. So let me just take that way. And pumps or sucks air through the orifice. Because of the restriction, pressure is needed to make the air flow through the orifice, and this pressure will produce a force opposing the motion. Often the piston is replaced with a simple diaphragm. And here is our air diaphragm, air dashpot, dashpot here, okay? Let me make sure that you can see it, okay? And a dashpot, oil, okay? Now oil. The oil is contained in the cylinder, and motion of the piston pushes the oil through restrictors in the piston to the other side. Again, pressure is needed to force the fluid through the restrictor, and this produces a force opposing motion. It can be shown that for both cases the force opposing motion, the damping force, is directly proportional to the velocity of the piston. The equation for this force is as follows. Okay. And here's our formula. Okay. The constant of proportionality, C, is called the damping coefficient and has units of, and here are your units. Okay. The value of C depends on the size of the restriction. And again, I'm using work from DJ Dunn, who is online and produces some excellent work, okay, which I found to be quite useful. So all merits to him and the work that he allows us to have access to. Now, damped linear vibration. Consider a mass suspended on a spring with a dashpot between the mass and the support. Now here is your dashpot, okay? Let's go up a bit more so we can make sure that we get it in full view, okay? And here we are, and here it is in full view, hopefully, okay? Your spring stiffness in Newton meters. This just shows the movement of your spring, okay? Here is your dashpot, okay? And here is what will cause this to slow down, thereby dissipating the energy of that movement. Okay. If a force F is applied to the mass as shown, it is opposed by three forces. These are the inertia force given by your formula for that, the damping force given by the formula for that, the spring force given by the formula for that. Then the total force is the result of this and applied by that as well. Okay. Because the vibration is free, the applied force must be zero when you let go of it. Okay. And again, here you have your, let me get my pencil out. Okay. That is your formula, and this is a linear second order differential equation, and it is much discussed in most math books. We make the following changes. First, divide each term by k. Okay. In the work on undamped vibration, it was shown that without a dashpot, a natural oscillation occurs with angular frequency. We may replace k over m with this and it's okay. Somewhere along the lines, I've got my lines has rubbed out. Okay, let me just get the rubber. 1 second, bear with me for a second. Let me just get these removed. Yes. Okay, good. Get back my marker. No, I don't want to use red, but red does not come up too good at all on my thing. Okay. Now these are formulas for you to apply for yourself and to make sure you understand the correct concept. So I'm leaving those formulations for you to find and to research and to make sure that you have the right concept and that you've learned it in your own style. Okay. Next, we examine the term C over K. We need to start with a definition. We will be using a term called the critical damping coefficient, and it is defined as follows. Okay. This has the same unit as the damping coefficient. The ratio is called the damping ratio, and this is defined as follows. Okay. This may now be developed as formulation. Okay. I'm leaving that for you to write out and to apply for yourselves. Okay. And to make sure you understand the concept. Now do your own research. Make sure you know what you're looking at. Understand the concept behind it. My style of learning and yours is going to be different, but it is important that you apply it for yourself. So I'm not going to try to tell you how to learn it. You need to look at this and put pen to paper for yourself. Okay. Can now replace the term by C over K in equation, and here we are. Okay. I don't need to say anything further because it speaks for itself. This is now a standard equation, and the solution may be found in standard text as, okay, A and B are constant of integration. Right, the resulting graph of displacement x with time t depends upon the damping ratio, and hence the value of C. Three important cases should be considered. Underdamped. This occurs when that situation occurs and this situation occurs. If we assume that t equals 0 and x equals c at the moment the mass is released, we get a decaying cosinusoidal oscillation as shown. The displacement is described by the following equation. Okay. The graph shows the result if the mass is pulled down 10 units and released. In this case, C equals minus 10. So it's been pulled down and then it's released. So, and you can see it's oscillating, but the oscillation dies out as time goes over a period of time. Okay. The natural undamped angular frequency, the damped frequency is f equals omega over 2 pi, and the periodic time of the damped angular oscillation is t equals 1 over f equals 2 pi over omega. Okay. Amplitude reduction factor. Consider two oscillations, one occurring m cycles after the first. The amplitude of the first oscillation at time t is this. The amplitude of the oscillation that occurs m cycles later occurs mt seconds later, so comes this. Okay. Amplitude reduction factor. Now examine the terms. Put t equals 2 pi over omega, and this becomes your next equation. Okay. Now substitute now again I'm leaving this for you to determine and call out for yourselves, okay? And at this level you should be able to do it for yourself. So I don't want to influence your how you wish to see it, because you may have a different approach, but the principle and the idea still remain the same. Critical damped. If the damping is increased, the oscillation die away quicker, and eventually a critical point is reached where the mass just returns to the rest position with no overshoot or oscillation. This occurs when that situation exists and this situation exists. The result is an exponential decay as shown. Okay. Now overdamped. Now here we have our graph. Critically damped and overdamped. Okay, overdamped. This occurs when deceleration occurs. The result is an exponential decay with no oscillation, but it will take longer to reach the rest position than with critical damping. What it means is that this kind of continues to vibrate a little bit before it settles down to a steady state. Okay, that's interesting. I forgot to put this into high definition. See, because and here we have a work example. Now I'm not going to go for this work example for you. It's quite straightforward and I don't need to be doing this for you. But let me just read what it says. A vibrating system is analyzed and it is found that two successive oscillations have amplitude of 3 millimeters and 0.5 millimeters respectively. Calculate the amplitude reduction factor and the damping ratio. And here's what you will need to be doing. Okay, I don't need to spend any time on that further. And here we have another work example again. Okay, a mass of 5 kilograms is suspended on a spring and set oscillating. It is observed that the amplitude reduces to 5% of its initial value after 2 oscillations. It takes 0.5 seconds to do them. Calculate the following: the damping ratio, the natural frequency, the actual frequency, the spring stiffness, the critical damping coefficient, the actual damping coefficient. Okay? And here's your solution. Now be aware that some of these calculations may be incorrect, so do the calculation for yourself. Make sure that the answer that we have here is correct, because there have been times when the answer applied to the formula did not come out correctly. Okay, so make sure that that is right. Also check your other mechanical books to ensure that the information we have here is correct and tallies with other books as previously mentioned. Okay, don't need me to do anything here. You should be able to do this now for yourselves. Okay, and we have example 3. Okay, and I'm going to read this here. A mass of 5 kilograms is suspended on a spring of stiffness 4,000 Newton meters. The system is fitted with a damper with a damping ratio of 0.2. The mass is pulled down 50 millimeters and released. Calculate the following: the damp frequency, the displacement, velocity, and acceleration after 0.3 seconds. Okay, and I don't need to go through this with you. You're going to make sure that you can see it. Okay, you can write it out for yourselves. Make sure I can pull back, okay, a bit. And you can see this yourself, okay. And here's some questions for you to do, okay, of your own accord. Torsional oscillations, okay. Torsional oscillations. The theory is the same for torsional oscillation. The linear quantities are replaced with angular quantities in the formula. These are mass, force, distance, velocity, acceleration. second moment of inertia, torque, angle, angular velocity, angular acceleration. Okay, and here's our torsional spring. Okay, that's what it looks like. And here's your damper, your dashpot. Dashpot for a torsional system would consist of a vane which rotates inside a pot of oil. The damping torque is directly proportional to the angular velocity, such that damping torque equals C omega. Okay, I'm just going to make sure that everybody can see that. Okay. Now, I don't need to read anything else here for you. You can read it for yourselves now, okay? Okay, and let me see if highlighting would make it any clearer or better to see. It might do. Let me just try that and see if I can highlight it in a okay. I've highlighted it there, so okay. So 1 second, bear with me. Let me see if I can. Okay. Okay. And here you have a work example. Let me see if I can highlight this for you. Okay. Okay. Hopefully making it clear to see. That's the idea. That's what I'm hoping for. Okay. And let's just change the color of the color if I can. Go with the green. Back and bring this down to here. Okay. Okay. Now I don't need to be talking on this, because this is not for you to be doing for yourselves. Okay. Basically. And let me just change the color back again to yellow. Okay, and we can then hopefully bring this into play. Okay. Okay, good. Let me just make sure I've got back up. My camera looks a bit weird. It looks like it's a bit lopsided, but I have no idea why yet. Just make sure that I'm not too far down. Okay, let's go up. Right. I'm just recapping now. Okay, so bear with me. Yeah. Okay, and I'm here. Thank you. Okay. Okay, okay. Okay, good. And I'm here. Now, work example number 4, all yours, okay? And your results should be here, I think. Okay. And self-assessment is here for you to do. Okay? And thank you. Now, I hope you found that useful, okay? And have a good day. Bye-bye.